Yes.
Is this on?
Yeah. I think we can hear you fine. Right. So thank you for staying for our last talk. So closing our stochastic numerics and statistical learning workshop. We're privileged to hear from Professor Diogo Gomes, who's the program chair for applied mathematics and computational sciences here at KAUST. Professor Gomes has had an illustrious career with prior appointments at Technical Lisboa, UT Austin, and the IAS at Princeton. And he's made sustained contributions to the study of mean field games. And for all the PhD students who are here, there's a very nice survey article on the topic. And today, Professor Gomes will be presenting on machine learning and price formation models with common noise. So the floor is yours.
Thank you so much for your kind invitation and for the opportunity to be here. You know, this price model is something that if you have been in the talk where I was speaking in the last 5 or 6 years, there is a 50% chance that I was talking about it. And every time there is a little bit more. Every time I think this is done, but every time there is a little bit more. And this is a really nice model because it's probably one of the simplest mean field games that you can set up. And it's also probably one of the most realistic mean field games that's closer to applications and closer to what we want to model. So what we want to do is to do the following. We want to study price formation, and we have a very large number of agents that interact via a price of a commodity that they trade. And the agents will trade. They need to meet a balanced condition, so you cannot trade freely because there is only a limited commodity supply. This may be deterministic or random, and in fact, the example that we are thinking about is electricity from sustainable sources. And so I'll talk about batteries and charges and charging rates and so on. But you know, if your thing is really soybeans, you can replace electricity by soybeans, trading rate of soybeans and soybeans stored in storage. So this supply can be deterministic or can be random, and we can tackle general trading and storage costs with some more improvements or slight changes in this model. So there is a lot of research in this area even before mean field games. For example, Kiwikaze and Mayame were looking at these problems where you try to store energy in space heaters. So in Canada, a way to use energy when you have lower demand would be to heat your house and use your water heater or your house as a heat reservoir, heat it when it's cheap, and then try to not heat when it's expensive and use the storage heat for the whole day. Now, in fact, I started this a bit later in the context of mean field games, and then the number of people, including my co-workers and Julian that's over there in the back, who have been working on these problems for quite a while. And I'll try to give you a bit of an overview of the model, of the main techniques and what can be done. So we have this price model. We have numerous agents. So today will be energy stored in batteries, tomorrow soybeans. Agents seek to maximize profits. They trade at a price omega of t, which is unknown, and it's determined by supply versus demand balance. And the supply is exogenous, could be stochastic, could be deterministic, and you'll see both cases here. So in the deterministic framework, what we care about is 3 main variables: the price, so the price is unknown; a value function. The value function tells you how much can you make if you start with X in our amount stored at time t, between 0 and t, and a path that describes the statistical distribution of the agent. So you have agents have a certain distribution of charges, and then you keep track of the distribution of battery charges along time. And so a price, a value function, a single agent tries to maximize the profit. This is the best he or she can do. And a path on the space of probability measures then tells how charged the batteries are along the different time. Now, on the mathematical side of things, don't be too scared if you are not used to Hamilton-Jacobi equations. I'll give you concrete examples, but what this boils down is to find a solution to this system of PDEs together with this terminal condition. So let me explain, and I'll go through the model. So we have the value function U is going to be a solution of a Hamilton-Jacobi equation. The distribution of the agents depends, and of course, this Hamilton-Jacobi equation depends on the price, because the profit that you can make will depend on the price. The evolution of the agents follows a transport or a Fokker-Planck equation, and there is an integral condition that couples these two equations and tells you, well, in fact, that the aggregate demand matches supply. Agents have terminal goals, so this is encoded in a terminal value for the value function, and we know where the agents are at the beginning of time. So this problem, the Hamilton-Jacobi equation, you can think of it as running backwards, but depends on this price. You can look at the Fokker-Planck equation or the transport equation, it's going forward, but now it depends on the price and depends on the previous solution. And then you have this balance condition that depends on everything, but you can think of it as the thing that determines price. And now you have a problem that's like a fixed point. You start with the price, you solve the Hamilton-Jacobi equation, you solve the transport equation, and then you solve the new balance condition, and you get a new price. And you want to get a price that's, well, it's stable and it's a fixed point of this process. Now, so what we mean by solutions, by the way, if I want to be a little bit more precise, is this is a first order equation, at least if epsilon equals 0. So in fact, what you want to do is viscosity solutions. If you know what viscosity solutions are, that's fine. If not, think suitable solutions for first order equations. Suitable weak solutions. M is a distributional solution of the transport equation, and the spot price is a continuous function, for example, that just matches the balance. And what I proved with my student João Saúde some time ago is that, in fact, under natural assumptions, what I mean is minimal convexity, coercivity, smoothness assumptions on various ingredients, then in fact we have a solution. We use a viscous solution, it's slip sheet semi-concave, and we have a distribution of agents, and we have a price. And in fact, if we have additional convexity assumptions, so if everything involved is convex kind of spirit, then you do have uniqueness and you do have additional smoothness. What I want to explain today is a little bit where this model comes from in the deterministic setting. I want to explain the key idea to get this fixed point in a specific example. And then I want to discuss the stochastic case and tell you what can be done both on the theoretical side and on the machine learning side of things, and why do we really need machine learning to do this. So on the stochastic case, what we have is, for example, and you can consider, for example, discrete processes, but here the supply follows a diffusion, and what you want to do is a stochastic Hamilton-Jacobi equation with terminal conditions together with the transport equation together with the balance condition. So the situation is very similar to the deterministic setting. The difference is that because now the price is a stochastic process, progressively measurable, and you are taking this Hamilton-Jacobi with terminal conditions, then you need a compensator to keep the progressive measurability of this value function. Very well. Now, but going back to the deterministic case, so we have consumers, they have a storage device connected to this network. They trade electricity, and you want to follow the old rule that you buy when the price is low and you sell when the price is high, right? And the way this is set up mathematically is that you have a trading rate that you control, and you have a cost, which is an integral cost plus a terminal cost. But this integral cost is in fact a very specific integral cost, which is the following. The trading rate gets multiplied by the price. This is exactly what the price means. Price means if you buy at a rate alpha, you pay var pi. And then you have an additional term that could be, for example, quadratic plus a potential. And you can imagine this term as being something that describes wear and tear of batteries or local price impacts. You can imagine that V of X is something that tells you, well, I have storage costs or I have constraints. Once my battery charge is negative, then bad things are going to happen. Or when my battery charge is above 100%, bad things are happening, and this could be encoded in this potential. So as I said, this term can be seen as the temporary price impact, because if you look at the previous, expression, when, oh, I'm struggling with this, right? Okay, so if you look at this previous expression, and if you factor alpha from this guy and this guy, what you can imagine is that in fact you are not paying the price var pi, you're paying a price which is a bit higher when you're buying and a bit lower when you are selling. So you can imagine that alpha is some kind of local price impact. You have a price, this price is quoted, but if you buy too much, then you start having price impact. So this is a possible interpretation of these costs. Now, you have a value function, which is the infimum over all bounded measurable controls. You build a Hamiltonian, and what we know is that in fact the value function, the infimum over all controls, is a viscosity solution of the corresponding Hamilton-Jacobi equation. And in fact, there is a little bit of additional information, which is the reason why Hamilton-Jacobi equations are important, is because they give you this what's called a verification criterion and give you optimal controls in feedback form. So in fact, at points of differentiability, and usually this thing is Lipschitz, so it's differentiable almost everywhere, you know exactly what to do. You look at your viscosity solution or your solution of the Hamilton-Jacobi equation, and then this tells you how much should you buy at this precise moment. So this is really the role of the Hamilton-Jacobi in this business, is to tell you what to do. Now, for example, just for concreteness, if we take a quadratic Hamiltonian, then we end up with a quadratic Hamilton-Jacobi naturally, and we have an optimal dynamics in feedback form. The nice thing about quadratic Hamilton-Jacobi equations is that they actually admit explicit solutions. In most of this business, you really don't have solutions in the sense of closed formulas, but for quadratic Hamilton-Jacobi equations with quadratic potentials, you can look for quadratic solutions if you have quadratic terminal costs, and you in fact can get fairly explicit solutions, for this problem. So this is a particularly nice class if you want to do computations. It's now, from the theoretical point of view, quadratic-like functions, so functions that grow pretty much like quadratic, are really the class where you can actually do theory, or at least where the theory is easier. Now, once you have a vector field, which is the optimal control, and all the agents follow these vector fields because these are rational agents, so they have this optimal strategy and they just follow the strategy, then the distribution of the agents or distribution of charges of the agents will solve a transport equation, which, if we are looking at the quadratic case, is also particularly simple equation. And now there is a trick in this business that you can also get Gaussian solutions out of this. So if you are in the quadratic case, you can get Gaussian solutions out of this kind of dynamics. And then if you require that the last constraint is that, well, you have an optimal trading rate, but you aggregate the trading rates and you require that demand matches supply. So the model that we get in the example is exactly a system of a Hamilton-Jacobi equation, transport equation, together with an integral constraint, and this is the meaning. Now, this for those of you which are familiar with optimal transport, this problem is really similar to the Benhamou-Brenier optimal transport. So if you remove everything in red, which corresponds to the price model, and replace it by anything in blue, you get the Benhamou-Brenier formulation of optimal transport. So the Benhamou-Brenier formulation of optimal transport is solving a backwards Hamilton-Jacobi equation together with a transport equation together with optimal transport conditions, which mean you are trying to take one measure into another probability measure. So it's trying to transport M0 into M1 with the least possible cost, and this turns out to be exactly in this framework. And in fact, you can see this problem as optimality conditions for a linear programming problem with center of mass constraints. So in fact, what you can think of this price model is some kind of optimal transport where you are not fixing the terminal cost and you are fixing some constraints on the center of mass. So that's another formulation of this model, is to say, well, I have a probability measure, I want to transport it somewhere. Because it's the price model, I don't care about where I land, but I want my center of mass to follow a prescribed path. And this is exactly this formulation. Now, as I promised you, I would show you a little bit of the proof. And I'm going to do the proof in one example, the proof of existence of solutions in one example. And well, it's not going to be a complete proof, but it's going to be to convince you at least that there is some hope of proving existence of solutions. And the difficulty here is that you have this system of equations. One starts in the beginning, one starts at the end, the other one starts. So terminal conditions, initial conditions, and they depend on each other. So there is no short time evolution. I mean, no Koshikov-Walewska kind of theorem that tells you, okay, if you are trying to solve for a tiny amount of time, you are in business. No, because these guys start separate, and to evolve one of the variables, you need the other one, and vice versa, and you have this coupling here that's not so obvious. So really, to prove existence, you need some kind of fixed point approach, or at least this is how we did it. So the idea is to show that you start with a price, and then you get a price, a new price, and this map price has a fixed point, right? So then you have the right price, the price for which this guy clears. To do that, you need some kind of compactness. So to prove that you start with the guess, you produce a new price or a better price, and you have a fixed point, you need some kind of compactness. You need to show, for example, that whatever you get, no matter how you start, here, you end up with a price that's Lipschitz. The next price is going to be Lipschitz. Now, let me convince you why this would be true in this example. And in fact, there is a lot of nice algebra that you can do fairly explicitly. One is this observation that, well, in this quadratic case, the agents want to maximize, well, their market impact plus costs. Let's say I take 0 terminal conditions to simplify my life. If you look at trajectories that minimize this, they solve the Euler-Lagrange equation, and in fact, you get a very specific trading rule, which tells you, well, essentially what I just said at the beginning. When price is high, you buy less, and when prices are low, you buy more. Right? So that's exactly what this thing tells you, is that trading rate goes the opposite way with prices. Again, solving this explicitly is only possible because I'm in this nice quadratic model. The next thing that you start looking is this. Well, let's look at this Hamilton-Jacobi equation. Let's differentiate it. And let's look at this quantity here, ddt of uxm. Well, why would I look at this quantity to start with? Well, because actually I have a balance condition that involves uxm, right? And m is a probability measure, so I can pull the price out of this integral, right? So I start looking at this quantity, and I start looking at its time derivative. If you look at its time derivative, what you realize is that the time derivative of that quantity is precisely 0 for a piece of magic that comes from integration by parts. Okay. How do you find this? You try it. And this is some kind of conservation of momentum. So it's not completely unexpected, but it's also not obvious because this system is time dependent. So it's not completely obvious. And in fact, what you get in the general case is a bit more complicated. You don't get, but once you have this conservation of moment, then the supply versus demand condition tells you that there is a relation between price and supply, and in particular, you get this linear price-supply relation. And let me tell you what I read from here. If Q is Lipschitz, then the price is Lipschitz, right? Because they are just a multiple of each other plus a constant. And in fact, what you can prove, in this case, you have an exact relation. In the general case, you don't have an exact relation, but you do have that the price is as Lipschitz as Q, right? You can make it a quantitative estimate that shows that the price is as Lipschitz as Q. And once you have that, then you have a fixed point. So you have existence. Now about solving and trying a couple of tricks. There is one trick that I particularly like, which is this trick of potentials, and you'll see why this is important in the end. And the idea is this: well, we have a system of two equations, but now we can look at the cumulative distribution function of m, which we call the potential. And of course, the derivative of cumulative distribution is m, and minus phi t is some kind of flow. And in fact, the way we understood this, that was interesting to look at this, is that, well, the transport equation can be written as a divergence in space-time. And then you can, by Poincare lemma, you can find a potential that integrates this equation. And now, once you introduce this potential, you are done with the transport equation, because the transport equation is going to disappear from your equations. You just integrate it. You just are left with two equations. You're left with the Euler-Lagrange equation, with the Hamilton-Jacobi equation, and you're left with the balance condition. Now, it turns out that there is something called the perspective function, which is you see J over mj is some kind of current, so J over m is velocity. So this is like Lagrangian times mass. It's like density of action or something like that. But if you introduce this guy, it turns out that if you look at this variational problem, and you see, because the idea is that J is going to be the flow of agents, so J over m is velocity. So what you put inside the Lagrangian is minus phi t, which is current divided by m. So that's kind of the intuition behind this guy. So look at this variational problem, which is some kind of minimize action together with the balance condition, and you try to rewrite the balance condition in a clever way that makes sense. So if you ask for this thing and you write down what the Euler-Lagrange equations of this functional are under the mass constraint, what you have is that they turn out to be equivalent to the derivative of the Hamilton-Jacobi equation. So in fact, your Hamilton-Jacobi equation is somehow the Euler-Lagrange equation of something. So there is a functional that we can cook up fairly explicitly out of the Lagrangian using the price as a Lagrange multiplier for the balance supply, such that actually, if I have a minimizer of this, then it will satisfy the optimality conditions. sorry, the optimality conditions are equivalent to the system that I want to solve. And then you can recover the solution. So once you have, let's say, a C2 solution of this variational problem, you can go back and produce a solution to the original mean field game. And you can do some of this under, you see, in some cases, you actually know that the mean field game has a solution. So what you want to do is just to recover it. So you're not worried so much about existence. You are worried about how do I compute it, right? And so, yeah, and in this case, you only have one function to minimize. So you reduce the dimensionality of the problem. And this is just integrating and writing down what the conditions are. So these potentials are a convenient way to do this. Now, another case that's also interesting and is this case of finitely many agents that we can do easily on the stochastic case. So you can consider an adapted L2 adapted stochastic process for the supply. And then what you want to do is agents will control their trading rate, but now trading rate is a stochastic process itself that has some L2 bounds. And you introduce a random variational problem. So you want to find a price which is progressively measurable, a control that's progressively measurable, all in these nice spaces, such that to minimize the action with the cost subject to this balance condition. And in fact, what you see is that the price can be regarded as the Lagrange multiplier for this constraint. And then you have, for fairly standard tools in calculus of variations, that you do have minimizers, and if you actually have a bit of convexity, you have uniqueness as you would expect. And then you write down what are the necessary optimality conditions. The necessary optimality conditions is pretty much the Pontryagin maximum principle. You have a backward stochastic differential equation for this adjoint variable. And the interesting thing is that there is a unique process. So this is a scalar function that's for every coordinate you have this identity. So the idea is that this guy is minus the price. So every coordinate of this guy is the same, and this is what comes from the constraint itself. Now, what is the key issue here is that, well, okay, so we have this nice theory, but really, except for quadratic problems, you cannot solve these mean field games. So unless you are exactly in the quadratic setting, and the quadratic setting has this nice algebraic structure that it differentiates a quadratic function, you get a linear function, you square it, you get back a quadratic function. So this kind of principle allows you to solve explicit quadratic problems, but in fact there are no other known solutions as far as I'm aware. I mean, this is really you can do quadratic, but then anything else it's out of solutions. And if you want to solve deterministic mean field games, I mean deterministic price models, you really don't need much, and existing technology can do the job pretty nicely, right? So because it's a one-dimensional partial differential equation that you need to solve together with a constraint. I mean, it may be a mess to write it down, but it's a finite dimensional problem, and you can easily discretize PDEs in one space dimension and time, right? But once you go to the common noise problem, then this problem becomes infinite dimensional. You have all these backward guys going out. So it's really difficult to implement numerically in an efficient way. Perhaps the easiest thing to do is to use some kind of binomial tree to expand the supply process and expand the progressive measurability. And actually I asked Julian to do this because I thought this would be would not give that good results, and then we could justify going for machine learning. Surprisingly, this binomial model works pretty well, although as you'll see, it has a lot of limitations. So what can we do? Well, we can, to obtain this numerical approximation, we can consider binomial discretization of my Brownian motion. So you start with the Brownian motion at 0, it goes up, it goes down, and this thing will branch out with various. Usually you'll need various layers, but as you can see, this tree grows quite fast. It's probably not difficult to run a tree of size 10 in your computer. It may be a bit harder to run a tree of size 20. You will not be able to run a tree of size 100 in your computer unless you are doing something that's not a tree, right? I mean, maybe you are doing things that are smarter and so on. You are pruning or doing some clever things, but I mean, I'm pretty sure you cannot store a tree of size 2 to 100 in any computer on campus. Okay, so this means that you cannot discretize time very finely, right? Now, what is a progressively measurable process here? Well, it's a function on the tree, right? So for every branch of the tree, you have a number, you have an amount of supply, and then you can discretize the time process such that in a way that the price also takes values on this tree, and the controls for each player are also values on the tree, and at every node we impose the balance condition constraint, and you discretize the cost function in a natural way, meaning you have sums over trees and so on. And this is an interesting thing, because once you start running the simulations, you'll see that if you divide this tree in 3 time steps, you actually have a pretty good, so binomial tree is a solid line, and what you get from solving the Hamilton-Jacobi equation in the quadratic case that we can solve is actually pretty close here. And as you go to a tree of size maybe 8 or 10 that we have in the end, is pretty much in very good agreement, which for me was a real surprise, that you can use so few time steps and have a very good agreement. So this is useful, for example, if you want to calibrate other models, because this tells you that these trees don't work so poorly that, and then you can actually implement them and use them as your validation model for other codes, which is an interesting thing. But and you see the price. This is a realization of the supply, and then you have a realization of the price for the binomial tree and for the Hamilton-Jacobi equation. You'll see that there is really good agreement with 9 time steps. And I think 9 is kind of the limit that we were getting. And then we were discussing, should we improve the code and make it run for 12 or 13 time steps, or should we do something else? And I think we decided to do something else. Now, so while the stochastic supply can be, and at least as far as our limited evidence can be approximated with this binomial trees, in fact, you have good agreement. The curse of dimensionality really limits the accuracy. You cannot go much more than what we have, and machine learning approaches can in fact improve resolution, as we show here, and this is what I want to explain. So what we did was to look at recurrent neural networks. So the idea of a recurrent neural network is that you have a single neural network that's repeated. So this is the same neural network. This is the same neural network. And what goes inside this neural network is the supply at the respective time. Well, in this case, this is the neural network for the control for the player I. So what you throw in is the Q at time 0, T0, the position of the player, the price, and the hidden state, which is originally initialized at 0. And then what you do is that out of this, you get the strategy for the player, you have the trading rate for the player, and you update the hidden state. So you get out of this a new hidden state, and this new hidden state is fed forward in the various in the same neural network. So the advantage is that this is for free progressively measurable, because at every state you only see present and past, right? So there is no issue. So that's one advantage. The other advantage is that in fact, with the training of these neural networks, what happens is that this hidden state probably captures the relevant variables. For example, if you are doing a quadratic price problem, you only need to know the average position of the players, or maybe the average and the standard deviation, but you don't need anything about second moment of the distribution. So in fact, if you want to solve a quadratic mean field game, you don't need to know a lot about the history. You didn't know what is the current distribution, what is the current standard deviation. You don't need third moments, right? So a lot of these models are kind of quadratic in the sense they grow because price impact increases as you trade more and you trade less. Storage costs, maybe you are not allowed to sell short, you are not allowed to store more than whatever capacity you have. So in fact, many of these models in practice will look very much like quadratic, which probably means that the only information that you need is first moment, second moment, and a few other corrections, right? And this is at least our interpretation. I mean, we don't have any evidence, but the interpretation is that these hidden states somehow capture this low dimensional information that's needed to understand the progress. So we do this recurrent networks for the trades, for the trading, we do it for the price, same strategy. And then what we do is this adversarial structure. So the agents, the network for the agent seeks to minimize, whereas the price seeks to maximize this functional. And this is exactly how Lagrange multipliers. I mean, one way to look at Lagrange multipliers is that you try to minimize some functional, and then there's a Lagrange multiplier that penalizes whenever your constraints are not satisfied. So this is exactly what this term is doing, and what we do is we train it using descent step in one of the variables and ascent step in the other variables. And let me show you some of the results that we have. So what can we take from here is that we have a supply. This is a deterministic case. We have a supply between 0 and 1, roughly. We have the price that goes around 1.5 amplitude, let's say. And if you look at the errors of this thing, when this is 0.03 or 0.04, I cannot see. And actually, I cannot see either here. But it's certainly 0.0 something, right? So you really have really good agreement in the absolute error and the relative error for these problems. So in the case of common noise, the way that we do is we train it like in the deterministic setting, except that for every gradient descent step, we discretize this SDE, and then we use a new sample for our supply in every gradient descent. And as I mentioned before, it preserves automatically progressive measurability, so we are not forward-looking in this case. Now, what you can do, we could think is this. Well, in fact, our machine learning framework returns an approximate solution of this of the optimality conditions with some errors, right? With some errors. And and one question that you may ask is the following: okay, so we have this machine learning framework, we produce some numbers, how do we know that they are correct? And there are two ways. One is to prove convergence. Say I take a large enough neural network. I have some error rates as whatever n goes to infinity. I have convergence, but there is something that's simpler to prove, which are a posteriori estimates. And a posteriori estimates is this idea that you look at necessary optimality conditions. You look at how much they are not fulfilled here and there, and then you try to get estimates for the error based on the observed lack of in the gap on the optimality conditions. The way that I like to explain this is the following. Think of x squared, okay? But you don't know that the minimum of x squared is 0. But you know that's a convex function. So you know that whenever its derivative is small, you are close to the minimum. So if you look at the number 2x, and this number happens to be small, you are necessarily close to 0. Okay? So this is exactly the kind of result that we have here. We have a convex variational problem. Actually, this is convex concave, but in the Lagrangian side, this is actually convex period. And what we can do is look at the gap in the optimality conditions and convert it into estimates for the price. And this is what we did there. And you'll see that there is a really nice agreement between the theoretical price from the Hamilton-Jacobi equation and the green, solid blue, and the green, which is what you get from these neural networks. And here you are really not limited by size. So if you want to run this thing with smaller time steps, you just run it with smaller time steps, because you are training always the same structure. So it doesn't really matter whether you use 1,000,000 time steps or 10. I mean, or certainly will not scale as a power of 2, right? I mean, it will get worse, but linearly worse, I guess. So we really have really good. So this is one realization of the price. This is another realization of the price. Now, another approach that I want to talk about is this price, this potential problem, and this is a really neat thing, because what we did was to say, well, let's look. Remember that the problem that I discussed, there was no expectation because it was the deterministic case. But we looked at a random functional, because phi is a progressively measurable function that minimizes the integral and satisfy the supply versus demand condition. And you write down what the Euler-Lagrange equations are, and you try to read what these Euler-Lagrange equations mean in terms of stochastic differentials. And what you conclude is that, in fact, you get a weak derivative of the stochastic Hamilton-Jacobi equation. This exactly the thing that arises from. So you have this potential, you minimize this functional. Out of minimizing this functional, you have automatically the transport equation, because this comes from this potential integrating the Hamilton-Jacobi, the transport equation. You get from the constraint the price, the balance condition, and then from the optimality conditions, you get the stochastic Hamilton-Jacobi equations. So you have one less function to approximate now, and you have a single objective function. So as before, what we did was we used this recurrent neural network. Actually, the story is that we started by this, and then we moved to the other problem. But I think it's more interesting to show it this way. So to approximate phi, again, we consider this recurrent neural network. You have a hidden state that contains information about path history and so on, and so here it is, the architecture. You get a hidden state, goes inside this neural network. You get the potential function at the various points. New hidden state goes in, and this is recycled. This block is always recycled. We have now an objective function which consists of the discrete approximation of the functional together with a number of constraints. For example, we want the distribution function to be the derivative in x to be positive because we want phi to be a cumulative distribution function. We want the balance condition to be satisfied. We want the terminal conditions to be satisfied. And this is a constraint that imposes that phi is the cumulative distribution function of a probability measure. So integrates to 1. And we aggregate these terms in a loss functional, and we proceed as before. So we consider a sample, we compute the loss functional, compute the gradient descent, and iterate. And at every step, we have a new sample. So this is the way that we force common noise here. And here it is an example. So we take a Lagrangian, which is quadratic, no terminal cost, terminal time equals 1, mean reversing process. Because this is linear quadratic, we can actually get a differential equation for the price, and in fact you get a really good agreement between these two guys. I mean, this is a deterministic case, right? And in the stochastic case, we have a theoretical form of the price which tells you that d omega equals minus dq. So one goes up, the other one goes down, which kind of reflects what you would expect. And you'll see here that there is a really good agreement again between what we get from the machine learning model and what we get from the formulas that we can solve. Okay, so and here it's just illustrating the approximation of this thing. So to summarize, we developed 2 variational approaches to price formation. Our formulations combined with these machine learning techniques provide a way to solve these infinite dimensional mean field games. And again, this is something that I would like to stress, that in the deterministic case, there is really no, I don't think there is an implementation of these price models, but there is no fundamental issue to be solved, because there you have PDEs in one space dimension, and you can run them. If I sit down, I can write the code easily. But here, these are infinite dimensional problems, so you really need this master equation or some alternative. And now we definitely got all these a posteriori estimates that tell you that once you get the results from these neural networks, then you can actually figure out how good they are and whether they satisfy your requirements. Of course, there is a lot of work to be done, including better architectures, better way to approximate, to accelerate. We didn't tackle convergence; we tackle a posteriori estimates. So it would be really interesting to have convergence rather than have just this. And I think this is a very good point to stop. So thank you very much. And if you have questions.
Okay. Someone in the chat was. Okay.
I don't think there are questions there.
It's just Emmanuel saying goodbye. All right. Who wants to ask a question first? All right. Well, while you think, I'll ask one. So in your supply SDE there, have you tried looking at with jumps? Is that possible?
Yes.
Yeah, it's possible.
Yes, it's possible.
Yet.
It's just that we didn't look into that. But
so, do you have any intuition?
Yeah, there is no fundamental issue in looking at jumps, except that I'm pretty sure as you write the theory and all these things, you'll face fundamental difficulties there, right? But this is actually a good problem because you have aggregate shocks in demand or supply.
Yeah. I'm not walking away because I'm scared of some of this.
Just a quick technical question. So you mentioned you approximate the Brownian motions by a polynomial tree Can you explain that? I didn't quite understand.
Well, you can approximate the Brownian motion by a random walk, right?
Yeah.
And this is represented, the process is represented in a binomial tree.
Because you write delta W equal square root of H, then delta W equal minus square root of H. What do you mean by it? So delta W here is the increment in the
square root H up or square root H down, depending on the time step. And you need to scale this with the time step.
All right.
I hope I didn't mess up the square root H, but it's actually square root H. I can blame Julian for that though.
Yeah, thanks.
No, I would take the blame.
All right. Are there any other questions? No? Okay, well then let's thank Professor Gomes again.
Thank you.
Thank you very much, Diogo. So I'm going to introduce somebody special now. And first I'm going to say a couple of words. This has formally concluded the last talk of the workshop. We're very pleased actually. And as we conclude this 12 days stochastic numerics workshop, I want to express my gratitude to all of you who participated, contributed, and were very active, right? So this workshop was conducted in a hybrid format, some people online, some in person, and overall has been a rotating public, depending on the topic. The first week was more general, the second week had a much more, say, focused flavor on computational finance, if you wish, and that in all contain essentially over 100 registered participants. And these speakers that we have, 32 talks in total, were very diverse, covered things from unbiased sampling using reversible checks or mean field optimal stopping, quite actually cutting edge in our area. I'm truly delighted by the passion that I saw and how much you conducted the poster sessions. We had 2 of them. And even though they were both scheduled for 1 hour duration, many of you stayed up to 2 hours and more, and I paid attention to that, and everybody was active discussing. That was great, and it's a pleasure to see how freely the ideas flowed, and you know, how many relations were created and collaborations started. That was very inspiring. Thank you very much. Our online participants also were active with questions. Technology for, pandemic, we can complain about pandemic, but actually has changed the way we conduct business, right? And nowadays we can have great minds participating as speakers or posing questions, and this is very enriching, very, very much enriching. We have the lead of a Swedish hedge fund participating in person with part of his team. So this was really cool. And for those who missed any sessions, you could revisit the talks. They are in our online YouTube channel that Carlon has posted beautifully every time somebody gives a new talk. Yes, and even the posters, some of them are recording snippets of 5 minutes for you to see. So as we bid farewell to each other, I remain very optimistic about this area. I saw a lot of intellectual energy and enthusiasm, and I look forward to welcome you back for future events. So before I conclude, I am honored to pass the floor to our KAUST Provost, Professor Larry Carrin. And until we meet again, may your research be fruitful and your intellectual pursuits bring you to great rewards. Thank you. Larry.
Okay, thank you so much, Raul. And I'm the last obstacle between you and exit, so I'll make this brief. So first of all, I kind of am in your field. Although I'm the provost at KAUST, my field is AI, statistics, and data science. And I actually got to look at a few of the talks, and I was quite impressed. So let me just say a few words about KAUST, and this has been almost 2 weeks of activity. So hopefully many of you have been here for a lot of that and have gotten a chance to see KAUST and hopefully see Saudi Arabia. KAUST is probably not what you think of. If this is your first time to Saudi Arabia and KAUST, my guess is it's not exactly what you thought. KAUST is a very unique place. Just to say a few words about that, you all have seen the beacon, I assume, right? And this is reflective of King Abdullah's vision for KAUST. As you might know, during the Dark Ages of the Middle East, the Dark Ages of Europe, it was the golden age of the Islamic world, right? And if you know that history, the Islamic world saved much of Western civilization, Western knowledge, Euclid and others, right? And so King Abdullah's vision was that KAUST would serve as a beacon to bring people from all over the world to study together around science, but perhaps more importantly, to learn about and of each other. And so as I looked at where everybody came from for this workshop, I think if King Abdullah were here, I think he'd be quite proud. And so thank you so much for coming. I hope for those of you who are out of town, thanks for coming. I hope you got a little bit of a taste of what Saudi Arabia is, and maybe you'll see a little bit more while you're here, Awula and other such things. In concluding just about the technical topic, again, my field is AI, and I think what you guys are working on is one of the very important areas in statistical science in academia. So one of the things that I have been thinking about is that AI and machine learning, which Diego was showing some neural networks, I think. What's happened now is an amazing success of the field of AI and machine learning. And as those of you who know, despite what you might read in the popular press, AI was not invented last week or last year. The field of AI was started in the late 1950s, and there have been a series of moments of excitement and then moments of despair repeatedly over decades. And these are in the field are called the seasons of neural networks. And you might be wondering why we have the term deep learning. Why do we even have that term? Because if you go look at the technology, it looks a lot like neural networks. And the reason is that for those of you who are younger, in the early 2000s, if you were to go to a meeting like this, like Diego, and say that you were using neural networks, you'd be laughed out of the room. Neural networks were in such decline that if you look in like the machine learning forums and just do neural networks in abstracts or whatever, you won't see anything in the early 2000s. And that was because that was the deepest winter of neural networks. But then, with the internet and with computation, there was access to massive amounts of data and compute. And these guys decided one more try, right? But they knew they'd be laughed at if they said we're going to do neural networks. So they had to reinvent the term. So they called it deep learning. It's a very cool term, but it's actually neural networks. And now I would say we're in the hottest summer, Saudi summer of AI, right? This is an amazing time for AI. But what's happened is that the technology has been so successful that it has been transitioned out of universities for the most part. If you look at where the action is, it's not a bunch of pointy head academics. It is Google, it is Microsoft, it's OpenAI, et cetera. It's an industry. And so, and that's because the amount of data you need and the amount of compute you need is just simply, you can't do it at a university. And so the thing that I've been thinking to myself is, what is the role of universities in this new world? Now, of course, we have to train the students that are going to go work at these places, and we need to find the appropriate niches within machine learning and statistical numerics, et cetera, where universities can bring real value. And so when I look at the subjects that you guys are studying, I think that you guys are focusing on the areas where there is still a lot of need for advance that will drive the next big industrial impact. So, I just want to commend you for some really nice work. I did get a chance to look at some of the talks on YouTube. I did actually look, and some very nice talks. Again, I hope everybody had a great time at the workshop. I want to thank Raul and AJ again and the team at KAUST for organizing this. And I hope that you guys get a chance to have a little bit more fun before you take off. So thank you so much. Okay, thank you so much. Thank you.
Well, okay, that concludes, as the Provost just announced, concludes the workshop. Thanks to all of you for your participation. Thank you.